strange transformation will lead to this nice system. I mean, they are not, so they are, these are not the contribution of the people who wrote this paper. It belongs to the old discovery. Okay. Long time ago, people recover this relationship. I mean, the transformation of these equations in some other, when they treat some other problems. Okay. And then people realize this, remember this, and they remember this, find that this reduction is useful. Okay, enough to be useful for these problems. So this is not developed directly on this problem itself. It's totally, it's a two different history. Okay, so in order to establish the equivalence of these two, and we want to rewrite this equation into a different form, because if you take the gradient to that, okay, you have the R Laplace U, then plus the gradient R dot gradient U. Right? And remember, R is a positive function, so if you divide this, there's the gradient R gradient U equals 0. But this one is just the gradient log R. Gradient log R. So I'm going to call this one the gradient log R by another name. So sigma is denoted by the gradient log R. This. Okay. So we're going to starting from here. So to check whether this, for every solution U satisfy this, whether this will imply this. Now, of course, we're going to in the complex D bar and a D operator, right? So here, so D bar is equal to dx plus I dy, and D is equal to dx minus I dy, right? So then you can see that how do you reduce the complex, the real equation to the complex equation? You are going to reduce this real operator, Laplace, and the gradient by the d and d bar, right? But this can be easy to see that you can cancel. So for instance, dx is equal to what? Dx, you add together, you have to, the price of dx is equal to the sum of these two, right? So therefore it's equal to d bar plus d over 2. Then dy, you can do the same thing dy. dy involves I here. So instead we make a subtraction. Okay, so d minus d, d bar minus d, then divided by 2i. Okay, so therefore I use these to substitute these real differential symbols. So particularly, you can see the Laplace is equal to d bar d, or equal to d and d bar. Okay, so therefore, and the gradient, so the gradient will be equals to right. So I can replace all these two differential operators by using the new operations. And then you plug it into this equation, you should come up with the system. Okay, so I'm going to show you more of these, about this case. Okay. So I'm not so sure we have time because I'm early. So I sketch the first step, and then next time we'll continue to this computation. So first you can see that this is Laplace, right? You can write this then plus, then you have the gradient. Gradient is distance. Okay? Then you thought the gradient u. The gradient u is just u by u plus du. now you can see, then you go here, so here you can see that the here is the gradient u is basically the same thing applied to the sigma function. Okay, so this is just coefficient here. So now you can, if you look at unknown function u, this unknown now is only attached with d bar and u. So here, if you mix simplification properly, then you should end up with this system. Okay, so I'll continue this next time. Okay, the